I'm just going to give you a disclaimer up front. This is going to be a little bit more of an advanced talk, so I might be going a little quickly through some things. Happy to answer questions afterwards, or come find me. I'll be in a floral. But I'm not going to hold back too much on that. All right. Hi. Yes. Yes. Hi, I'm Aneesh. I'm a proud Nix user for almost a decade now, since college. My claim to fame is that I wrote the original implementation of override adders, which we all use every day, back when it was 4 lines of code. But for my career, I've been in the industry almost the same time, and I've been really focused on developer experience and developer tooling. Previously, I was at Lyft, leading their languages team for 6.5 years, and since about a year ago, I'm at Anthropic, which is an AI safety research company. We make products like Claude, and as well as we do AI safety research, such as Golden Gate Claude. If you haven't tried it out, we put out 3.7 on it last week. It's a hoot. And at Anthropic, I'm on the builds and deploys team. When I got to Anthropic a year ago, they told me we used industry standard tools, obviously a lot of Python because it's an AI shop. We're using Kubernetes, and at the time, we used one image for everything. That image was 35 gigabytes large, uncompressed. Normally when people talk about a large Docker image, they're talking like, oh, a couple hundred megabytes is big, like a couple gigabytes is enormous. This was another level of very large. There's good reasons for it. ML libraries will monomorphize their kernels for different hardware architectures of accelerators. You have researchers adding things that they needed one time and maybe didn't remove since then. There's good reasons for it. But there was also just some inefficiencies in the build that hadn't been cleaned up. When I got there, I pretty quickly cut out about 20% of it, but there was still a pretty big image left, and this causes problems. Build times are slow, pull times are slow, push times are slow, and we were seeing 4-minute times to pull anything, which is really painful. It also meant that the rebuild times were almost an hour. This was slow enough we couldn't run in CI, and we actually had to have a manual process for who was going to build next. Most of our code is Python, so people didn't have to rebuild so often, so it wasn't too bad. But a few months into my tenure, we had a new, very high priority initiative that required compiled software where people were going to be changing this multiple times a day. And so we knew that this existing process was not going to work for us. So today I'm going to talk about kind of our story from escaping Docker because it wasn't going to work, obviously going to Nix. We're going to talk about nix-sidecar, which is the thing I built to address this. And then we'll give some closing thoughts at the end. Part 1. Docker files don't scale. This is something many people have talked about, so I'm going to brush through this a little bit quickly. Both this conference today, last year, all over the place. One of the problems they have is there's not really any abstraction beyond the abstraction of a parent image. You can have a script that you call, but if you use all the best practices like bind mounts and secret mounts, it could be 10 lines just to have, conceptually calling one script, copy pasted across many Docker files. You have ability to do parallelism with the multi-stage feature, but it's very unwieldy, and it's hard to keep track of which things are in parallel. Because of legacy packaging managers, some things just cannot be done in parallel easily. And it also causes non-reproducibility. We've had incidents where an apt repo changed their GPG key, and you didn't notice for 3 months, and then you made a change that busted the layer, and now everything is broken. And it's also causing very large images. With legacy package managers, with apt-get, you might have a package that spots things into user lib, into etc, into opt, into somewhere else in the file system, and it's very hard to pick and choose specific things to just say, oh, I only need the library part of this, and I don't need the binary or the man pages. And the biggest problem is that it's a very linear thing, so if you change one layer, all the layers below it are going to change. Let's look at some graphs to talk about what I mean. Here's a graph of our layers in our Docker image. It looks not too bad, flat-ish, kind of increasing, but the problem is that this is a log graph where every increment on the vertical axis is 2 orders of magnitude. And so the actual layer distribution looks like this. You have 1 or 2 very fat layers, and everything else is much smaller. So if you change a config file and it's before that layer at the end, then you have to change half the Docker file. And this is super painful. A lot of times, that layer might be CUDA. This is painful. It's the nature of software. What can we do about this? Enter Nix. Nix has abstractions. We can just say, yes, I want to have the build tools, and I also want the interactive shell tools, and I also want the production job tools. We can do things like it's built in that you have to pre-declare your dependencies. They have to be hashed. You have parallelism built in, both within a build and across different builds. Nix natively understands which dependencies are build time dependencies versus runtime dependencies. So you can build with, say, LLVM or Clang or Rust and then not ship that to production. And because it knows what specific dependencies are true dependencies, you don't invalidate the whole world, only the things you need to do. The great thing is people have already wrapped this up into something called Docker tools inside Nix packages. And this is a really great tool, and there's a lot of talks about it, but it is not perfect. The problem is that even with Docker tools, You are building a Docker image. They actually got standardized as OCI images. And so the OCI format is kind of the standard name for a Docker image. And the problem is that these images are limited to 128 layers. And so if you had a 35 gigabyte image, if I had that previous graph was entirely 100% flat, that's still in the best case 250 megabytes. And if you change like 2 or 3 text files, to download 250 megabytes is a huge overhead of just like reading, writing, caching amplification. And really the only solution here is to be able to go finer grained and to break this 128 layer limit. The other part of this is containerd. Containerd is kind of the actual like runtime, container runtime part of Docker that got extracted out into a separate project, where Docker itself is now like more the UX and the interface. And the thing with containerd is that when it's downloading an image, it can download the layers in parallel, but then after that, it has a serial step where one at a time, it goes through each layer and extracts them. And this is just part of the design of the software. It can do a multi-threaded extract of any particular layer at once, but this is a problem that should be embarrassing parallel. Like this is just like bananas to me that this, like the industry standard just like has this bottleneck in there. Turns out Nix can also solve this problem for us. Derivations are natively finer grained than a Docker layer. You can have multiple outputs, or you could just like make your own outputs, or sometimes they're just natively like in a layer you might apt-get the whole universe, whereas in Nix those would each be separate derivations. There's also no limit on really the number of derivations. You're limited to 128 layers in a Docker image, but in Nix you could have easily thousands or tens of thousands of derivations for your software. And again, we have baked in parallelism when you're copying closures around, when you're fetching from a substitutor, when you're uploading things. All of those are going to be baked in. Compressing is also parallel. Like there's no like artificial like you must go one layer at a time. And so the solution for us was to say, for this new initiative, let's not use Docker. We're going to build a software with Nix. You can do development build on your personal developer machine. You could be building it in CI for a production workload. The key part is then you upload it to our internal Nix store, and you do not upload it into Docker. You do not build a Docker image. You do not go through this manual coordination process. You don't wait an hour for the whole thing to build. You just upload it into the Nix store, and then you can run tests on it or do whatever else you need to do in CI. And instead of having this baked into the Docker image, we instead have a reference. You could store it wherever you want to like, this is the Nix store path that this job needs to run at runtime. And when the job starts up, you will fetch that at pod startup. And so it's not that like the container will start with the like image that doesn't have any of the Nix bits, and then we will download the Nix bits, and then your actual like user space code will run. And so this essentially like gets out of the Docker paradigm entirely for this part of the software and lets you kind of escape some of those shackles. One key thing here is even though it's like getting down at runtime, Nix environments are great. Usually the only thing you need to do to like make it available is to prepend it on a path. And so we don't have to like bake the path that we need to use for the Nix store derivation in anywhere. We can just say, oh, activate the path, put it on path, and just say like run my cool binary, and it will be on the path for you. Let's talk a little bit more about how we made this actually work in production. You start with some code on GitHub, and in CI, we'll put it up into object storage, a bucket here. This is probably S3. It turns out that when you run software in multiple regions, you probably want to have per region replicas. So we automatically replicate those to individual buckets, so you don't have to do cross-region reads, which can be slow. And then additionally, we have a cache in each region, in that going to object storage can be slow. The built-in S3 code in Nix does work, but it's not the most optimized for maxing out the bandwidth that you have available for you. And putting a cache in there, especially for some of the metadata files, makes the operation much faster. And then finally, at the end, we have our job here, Kubernetes pods that are actually doing the fetching. So they're fetching from the caches, which have everything auto-replicated. So the developer, they put up a PR, say I upload stuff, it gets replicated, and then their job is able to pull things at startup. Let's talk about the results. I previously said we had 4-minute pull times. That was for our entire image. For this initiative, it was about 10, 11 gigabytes of software. So I've proportionally scaled the like before number. With Docker, it would be about 70 seconds to pull that. What we saw is when we just had the one S3 bucket, like the one Nix store, it took that down to 45 seconds on its own. And when we added a caching layer on top of that, that took us down to about 15 seconds for pulling down software every time. So this was like a great win for our developers. We frequently have jobs starting, whether it's in CI or just I want to test a thing or a production workload. This is like 2-3x improvement, which was really nice for a lot of people. Great, everything's solved. What's more to do? Turns out we had a problem. with containerd, if you've pulled an image already and you run another job on the same node, then that image is already present and you have a 0-second pull time. It's already there, it's cached, you don't have to do anything. With us, we didn't have that, and so we were just fetching at startup every time, and it was taking 15 seconds. 15 seconds is actually like not that bad, but the real problem is the bandwidth usage of like you're downloading all the stuff, and then you're throwing it away, and you're downloading the stuff, and you're throwing it away, and this just is not useful. And so the problem is that like this can take a lot of bandwidth when you have like very large jobs that are running across an entire cluster, and then your cloud providers start to get a little sad about like you're using too much bandwidth. And so the solution is just like don't throw it away and keep it stored on the node. And so I want to talk about how we made that work. Before we talk about like the actual solution, I want to talk about some of the requirements that we had. You know, in a production workload, we just need to have the actual software running, and so we can have a /nix that's entirely read-only. We just have the paths. You don't need to use runtime nix. Like nix-var can actually be empty. In the original implementation, I just didn't populate nix-var because I'm like old school. I didn't realize that in the last 10 years, we added a feature called the user to root, where if nix detects there's a nix-var that doesn't exist, it will just make its own under like your home directory for a temporary usage, and it will let you use runtime nix, which I didn't realize. And so by creating a nix-var that's empty and read-only, you tell Nix like, hey, you should not do any runtime operations. So that was a little wrinkle, but the key point is like for you know, a production workload, we don't really care about having any runtime nix, but for developer workloads, we do need it available. So we need the nix store to be read-write so you can add things on the fly. Like if I'm a developer and I want to pull down like a dev tool that I don't want to ship into the image, I should be able to do that. And also the database needs to exist. Like not only have we downloaded the nix store paths, but we need to tell Nix like these paths exist. So if you try to garbage collect, it doesn't delete all the things you just downloaded and make you able to download new software as well. So with that kind of understanding that we need to be able to support runtime nix, let's talk about some of the solutions that we looked at before we went our own way. First one is RFC 152. This is a thing called the Nix layered store. You may have originally seen the blog post about super colliding Nix stores. And the idea here is that this is actually merged into Nix now as experimental, so this is the first place we looked. And the idea here is that you essentially have two Nix stores. One would be on the upper store, which is going to be inside your container. So this is where, as a developer workflow, you could add new things at runtime. And then you would have a lower store, which is going to be on the node of like, I pulled some stuff down, this is cached, and that's going to be on the lower store at the bottom. And so at runtime inside the container, Nix layered store is able to say combine both of these stores into one like logical store, and then also combine their databases together. And so on the surface, this seems like it works. Download things into the lower store, use it for production. In development, you have the upper store. There's two big problems with it for us. First one is specificity. With this approach, anything that's available on the host is also available inside the container. And the problem is sometimes people will just say like, I'm going to poke around the file system, find a random path that like happens to exist, say jmalloc exists here, and then go and just like hard code that path in their application. And then it works in their job, so it must like ship it. And then you run it in production on a different node that hadn't happened to pre-download that, and then everything breaks. And so we want to be very specific that only the paths you've declared you need to have available to your job are available, and not just whatever's on the node. And so for me, specificity is important, like less so in developer environments, but especially in production environments. The real deal blocker, though, is garbage collection, in that there's no support for garbage collecting the lower store, which, again, is the one that's living on the node. For the original use case of the layered store where there's a big persistent disk, this was actually fine. They just made a new one every time. But for us, we actually need to keep track of the SSD usage on the node. We've had incidents with other software where we've run out of SSD and it's a real issue. And so it's important to us that we're able to garbage collect things while there's possibly multiple jobs running on the node. And so unfortunately, we weren't able to just use Nix layered store out of the box. Nix Snapshotter. This is the next place we went. Nix Snapshotter is an open source tool developed by PDT partners. Shout out to Edgar, who did like most of the implementation. He gave a talk about this last year at the New York Nix meetup. It's also open source, very helpful. And in my opinion, it's probably like closest to the state of the art, basically, in the industry right now. The way this works is a little bit different in that this is hooking into containerd, which is something that we've extracted from Docker. So the kubelet, which is the part of Kubernetes that runs on each node, actually interacts directly with containerd. And containerd has a concept of plugins, which are called snapshotters. And so Nix Snapshotter is a plugin that integrates into containerd. And so in your Nix image definition, your Docker image definition, you would say like, this has dependencies on these Nix store paths. And then when you want to run that on a Kubernetes node, Kubernetes will say, hey, containerd, fetch this image. Containerd will say Nix Snapshotter fetch this image, and Nix Snapshotter will download that code via Nix, not inside the image. Like the Nix store paths are not baked into the image. There's just a reference like I want this path, And Nix snapshotter is going to download it to the node and then set up some file system for the container and then it'll go. This is the same thing that Containerd is doing natively with like say overlayFS, but now we're using Nix to do it. This solves the two issues that we had with the Nix layered store. The first one being specificity. Nix snapshotter will use bind mounts so that it will only bind mount the specific paths that you requested in your image definition into the file system that it sets up for the container. And so even though other paths may be cached on the node, only the paths that you requested will be available inside your container. It also has garbage collection support because it's hooked into Containerd. It understands the container lifecycle and which containers are alive or no longer alive, and consequently, which garbage collection routes are alive or no longer alive. And so you can set up your own like Nix native garbage collection policy of like on a schedule or once a day or like manually, but it natively understands both the container lifecycle and the Nix lifecycle, and so you're able to handle garbage collection. Like I said, it's really great, so what was the issue? Two big ones. One, we run on a couple of different cloud service providers, and for various reasons, we weren't able to customize Containerd in this way, and so we weren't able to deploy Nix snapshotter, which was a problem for us. It kind of blocks us from using the tool. The other problem is that I just have an aversion to running services. This was really a change for me coming to a research org, but like we are much less focused on services. It just makes more sense for the research workflow. And in my head, I was like, why should I run a Nix daemon service on every host if I don't need to? Now, don't get me wrong, I love Nix, but updating these AMIs when they're not based on NixOS would have been a huge pain to manage, and it would be much easier for me if I did not have to manage a piece of software in these like cloud AMIs. Like Google doesn't even let you adjust the AMI whatsoever. So let's talk about nix-sidecar, which is basically Nix snapshotter and user space. So we get all the same benefits without having to change the node or Containerd. So if we think about a node, we want to have an SSD on there so it's fast. And if you start a job, say a pod in Kubernetes, we were going to inject nix-sidecar. Nix-sidecar is actually an init container, so it is going to start before your main container starts up and start executing immediately. And what it will do is it will have a mount from the host SSD available, so it can see all of the nix-stick stuff that's on the host. And it also sets up an empty volume called nix container, which is the file system that it's preparing for your main application container. It'll say, okay, what are the Nix store paths that we need for this workload? And it will download them from our Nix store onto the SSD. And then the next thing it will do is it will set up bind mounts in the same way that Nix snapshotter would into the Nix container. So whereas on the SSD you might have 100 paths from the last 50 jobs that ran, here we'll say we're only going to bind mount the 20 paths that we care about into this Nix container. And then additionally, if it's a development workload, it'll set up the Nix database and make things read-only for you, or read-write for you. Then at that point, the application is started, and as far as the application is concerned, it just got a file system that looks the way it wants it to work, with the Nix store and or Nix var already populated. It didn't have to think about anything, and so the application can just run. And meanwhile, nix-sidecar still has access to the Nix container mount, so it can GC old paths while the main application is running at a very low priority, so it doesn't affect the production workload. This is not as trivial as it sounds. There's some subtleties with bind mounts. One of the things you'll have noticed in the picture is that we had nix-sidecar as one picture, we had the application, and then we had the volume over here. It turns out that if you create some bind mounts inside a container, they won't automatically show up in the other two places. You have to use a Linux kernel feature called mount propagation, and so there's a flag for this in Kubernetes, mount propagation, that you need to enable. Otherwise, you get an empty /nix store in the container, and you're like, why did this happen? This also requires running the container with privileges. For us, this is not a problem security-wise because this is a very constrained surface area inside the Nix sidecar. It has like a 50-line bash script and it has one job in its life, and it's very easy to control. Like, it's not running any user-controlled code whatsoever. And so for us, this was an okay trade-off. And the last thing is that Kubernetes gets really mad if you set up a bunch of bind mounts and you don't clean up after yourself. So while a traditional init container would just start, it would run to completion, and then it would exit, and then your main container starts. We actually use a feature called sidecars, where you start the init container, and then it just keeps running, but once it signals it's ready, the main container starts. And so then at the end of the lifecycle, after the main container ends, we're able to go and clean up all of the bind mounts we did so that Kubernetes doesn't stick your pod in error terminating forever and that you are just wasting resources. And so this is also a key part of the equation. Let's talk about results. Here's a graph from a subset of our infrastructure over about a 24-hour period. You can see the biggest spike is at the 0-second mark where we had everything cached and we didn't have to do anything. You'll see smaller spikes where we had either a partial download or maybe had to do a full download because it was a new node. There are a few outliers. We're still like actively developing this. I've been like merging stuff on this like this morning. So it's live in production. This is more about optimizing things. And so it's certainly something we're actively working on. There's a lot of things that we want to go here. There's so many, in fact, that I'm not going to go over them, and I'm just going to give you an idea of how many things that there are to do. There's a lot of cool things you can do, but the nice thing is most of these are like not specific to our company. They're just standard Nix things that you could be doing at any deployment. I want to leave you with some takeaways. First of all, Docker is an industry standard tool, and it's really great. But there's also inherent limitations in the format that you don't need to constrain yourself with. For most workloads, it's fine, but if you're running at scale, you can escape, and Nix is a great tool that lets you escape those shackles. That does mean that you need to do some of your own building. You'll need to kind of do some self-assembly. It doesn't all come in one package. But if you go back to kind of first principles and think about, oh, yes, I shouldn't throw away the stuff I downloaded, you can build your own solutions and have a really successful experience at scale. I'm Aneesh from Anthropic. We're hiring heavily across a number of infrastructure roles, so if you're interested, come find me afterwards. I'll be in a floral shirt, happy to talk. Otherwise, happy to take questions. Yes, in the green hoodie. Question was, what base image are you using for the sidecar and your main pods? For the sidecar, ideally where I would like to end up is you have a single binary that's just the Nix static binary that's been built by Nix. That was going to take a little time to get set up, so we went with Alpine. But we can't use a Nix image directly, because if the container has its own Nix/Nix, then we can't mount the host/Nix directly. You can like hack around it, but it's kind of painful. And so we actually are using Alpine there, but the plan is to eventually have a single static image binary. The application container, it doesn't matter what the OS is, in that we are just giving it a Nix store and it can run whatever it needs. So we actually have a variety of different things depending on the workload. Yeah, I mean, I think for the build side, it really depends on what you're building. Like some of these native compiled code can be like pretty large when we've got some forks of some large open source projects. So if you're like changing like a root derivation, it might take a long time. If you're only changing something in the end, then it'll take like less than 2 minutes. But the idea is that when you put up a PR, we'll do an evaluation to see which things need to be built that aren't in the cache already. We'll spin up some jobs to go build those things and we'll upload them. And it really just depends on like, did you change a root level dependency or like something at the end, like any other software. Does that answer your question? Okay, sure. You're right there. Great question. Nix-sidecar is an internal-only thing, but the good news, it's only about 200 lines of code. Most of that code is pretty tightly coupled to our deployment system, so it doesn't make sense for us to open source. But it's also something where the initial implementation took about like a day and a half, and it's like not a lot of code. The key part is like understanding all the techniques in the big picture in your head. Once you have that picture, it's like there's just not enough value in it to kind of justify open sourcing, in that you can do it on your own like pretty quickly. Does that answer your question? Awesome. In the back. Yes. So this is what the nix-sidecar is doing. It has a host mount from the node, and so when it's downloading things, it will download directly into that volume on the node. Yes. 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 And the front.
You described how using Docker you ended up with this problem that you had to solve, and so Nix was the solution.
Mm-hmm.
I'm curious about what was the inflection point of you going to look for a solution, and what else did you consider?
Question was, what was the inflection point of going from Docker to Nix? So, I mean, as soon as I showed up, I knew that the Docker thing was not working for us. But, I was like, all right, we're going to do Nix. We're going to start moving. We started moving right away. But then a couple months in, we had this high priority initiative where they were developing compile software. And so for most of the company, if they're using Python, they're not changing the image that often. But for this, they were needing to change it multiple times a day. And so they needed like a quicker solution. And so it was like time to hit the eject button on Docker and like move them straight to Nix. They've had a couple of rough edges because they've had to use Nix in the like full glory of Nix. But they have some smart people there, so it hasn't been too big of a deal. Does that answer your question?
The follow-up was, what else did you consider?
What else did we consider? Great question. So really the key thing for me is that you need these fine-grained dependencies that you can build, cache, fetch in parallel. And there's other tools that have similar shape. It could be a Bazel, it could be a Buck2, it could be a Pants. But the problem with all of those is you have to write the entire universe from scratch because there's very few existing build definitions. With Nix, the great community, mostly college students, has written a lot of those already for you. And so it was just a natural choice. We also had a lot of folks that were just Nix fans. Like I don't personally like some of these other tools, but just from the largest and freshest package repository in the world, that was a clear winner for me. One more question. Yes. So the question was about regional replicas. Yeah, so the question is what is going on with all the layers of caching? So at the S3 layer, it's different on different cloud service providers. I'll just use AWS as an example here. There's just like a main S3 bucket, which is the main like primary Nix store. But we just have some regular S3 buckets that exist in other regions where there's a feature to have things auto-replicate in AWS. And then we're also using cloud technology for the cache right now. We're looking at replacing that with something internal for like out-of-scope reasons, but we're just using an AWS product for the caching layer that also is auto-synced from the S3 bucket. And then the node level cache is kind of nix-sidecar. It's not a running persistent service. It's we download things to the host and then we just don't throw them away. Nix-sidecar runs as a container, but it has a host path mounted from the host SSD, and so it's able to cache onto the host. If the machine is recycled, do we have to restart? Like yes, if it's a new node, you will have to download from scratch. One more, are we out of time? All right, I think we're out of time there. Thanks everyone for coming.